Thank you, Morita Sensei. And it's my honor to be here to present my results. And I'd like to thank Senkoba Sensei to invite me, give me the opportunity. And my talk is about RIXS. Actually, nobody knows about RIXS, but this is a very famous X-ray spectroscopy in our field, very narrow regions, but I will explain a bit. RIXS study on hydrogen-bond network water at interfaces. And I will talk about, half of my talk is about bulk water, and the last half is about interfacial water. This is the collaborators, and the members in the University of Tokyo, and the sample preparations were given at the Kyushu University, and some of the members are already here. And I'd like to acknowledge the members who helped with the experiment and analysis of the spectroscopy. As anybody knows, the hydrogen bonding is the connection between the hydrogen and in this case, the water case is the oxygen, and this is directional, and in ice phase they are four coordinated in a tetrahedral coordinations, and that has a directional bonding, and that makes the property of water very complex. And about the structure, anybody knows that the structure of water has been known from the X-ray diffraction, because X-ray diffraction gives us knowledge about the distance and the number of the bonding from oxygen to oxygen. For example, in ice phase, we have 2.7 nearest neighbor oxygen, and the number is around 4.4 in the liquid phase, and around 4 in the ice phase, And at a longer distance, the liquid phase has blurred structures compared to ice phase, because ice phase has long length order, while in the liquid phase they are thermally distributed. But still there's a structure here, and from this, it is said that the water is basically at the nearest neighbor 4 coordinated, like ice. However, the X-ray diffraction is not looking at the bonding media, but just looking at the electronic density of the oxygen core. Then this is just looking at the distance around here and the number of the coordination. However, what we should see to discuss the hydrogen bonding is the glue that is connecting the water molecules, and that is the balanced electronic structure. That is the electronic structure. Then we chose another method to see the hydrogen bonding. This is the X-ray spectroscopy using soft X-rays that resonate to the oxygen KH. K is the deepest core of oxygen. If we use this X-rays to excite the water to the unoccupied state, this is the electronic structure of water molecule, and hits the oxygen 1s core to the unoccupied states. The core is very unstable, and in a femtosecond, the balanced electrons will decay back to this core, and we can see the distribution of the electronic structure of oxygen. This is a 1s core, so we can see the 2p type balanced electron structures, and this will be affected by the hydrogen bonding. So in that way, we can see the hydrogen bonding. And there are a lot of methods to see the structure and the dynamics of water, and among them, X-ray spectroscopies are very crucial, because they can, of course, discuss the number of hydrogen bonding, but also the distortion of the hydrogen bonding. The distortion here means if we have the 4 coordination, tetrahedral coordination is the symmetric coordination. But if we have some, for example, some pressures to the water, the pore coordination will be distorted. And X-rays are very sensitive, this kind of asymmetry along the one water molecule. And we can discuss add some information to this, a lot of methods as a distortion, hydrogen bond distortion. Then we can probe many types of water using X-rays. For example, by adding some water using humidifier, adding water molecules gradually and looking at the interface and gradually growing the bulk water. Then first I just show you the bulk water. This is the result of the water in 3 phases. This is the gas phase water. As you see, there are 3 peaks corresponding to 2p orbitals. And this is the gas phase. We have 3 bondings. But in the ice phase, we have 2 phases, two peaks. And 3A1 orbital will be here, but they disappeared. Because this is an A1 symmetry that is not allowed to transition to the 1s cohort. In the liquid phase, we have a doublet peak at the highest orbital. This is very strange, but naturally this can be understood because the gas phase has this 1b1 peak, and that corresponds to the higher lobe of the 1b1, while the lower lobe should gradually connecting to the ice phase. Then we interpreted this factor that the water should have 2 phases and 2 structures. And increasing the temperatures, you see the increase of the higher lobe, and that is very natural to think that this is the broken hydrogen bond, and this is a tetrahedrally coordinated hydrogen bond. And we did a lot of work on this, and I will skip all the details, but we interpreted now that the living water is a very strange term, but the water we have now at ambient pressure and ambient temperature, maybe there are 2 phases. One is the tetrahedrally coordinated ice that could be related to some substances that Hamaguchi-sensei told us that the ice, nano ice, I don't know, but actually we have this kind of species, and the size was measured by X-ray, small angle X-ray diffraction, and that was actually 1 to 2 nanometers. That just matches with that Professor Hamaguchi said. And there should be some conditions around here. And there's a critical point here. You know that there's a pressure, temperature. We have the second critical point. There is much discussion about the position of this critical point, but at least there should be some fluctuations of the 2 structures in this region, and we are here. So that's what I see here. Then, as an interface, things are changed. So we prepared the interface using a polymer brush. This is a polymer, and the separation of each polymer is around 1 to 2 nanometers. That matches with the size of the nano ice. Then we looked at the water inside this polymer. And the polymer is like this. This is ammonium ion, and there is a counter anion here. And there is separations at 1 to 2 nanometers. Then we see the structure of water using X-rays, and this is the experimental setup. But I don't have much time, so I will skip the details, but we put the sample on the ambient pressure side, but X-rays should be in the vacuum side. We have some very thin window that can penetrate X-rays, and we add some humidity using the machine and change the humidity. We looked at the spectrum. And finally, we identify the water inside the polymer brush. Then the probing depth is around the length of these polymers. And then finally, the result is here. The bulk liquid water is a doublet here. While in the confined or the water inside the polymer brush has only one peak here. And this is very similar to the ice phase. I can show you here. The blue line is a crystalline ice. We only have one peak here, while in the liquid phase we have doublet. And the polymer inside, water inside the polymer has only one peak. Even this is the ambient temperature. It's very strange. Very strange, but this is completely coordinated. No distortion of water. And this was previously predicted by the IR spectrum. Another group from Kyushu University did the IR measurements of this polymer brush. Then they looked at the red shape of this OH stretching band, and the center is around the ice, just mapped to the ice phase. But the SN ratio was not so good, and background was not so good, but now we confirm that this is real ice in a polymer brush. And we interpret that not only this one peak, but we also have shoulder here. And this corresponds to the distortion of the hydrogen bond I explained in the introduction. So the water inside the brush should be tetrahedrally coordinated, completely ice, but completely distorted. Distorted means some ordered distortion. Then, yes, we have a small pre-edge in the absorption, and this also corresponds to the absence of the broken hydrogen bond. Then, now we change the spacing of the polymers using different graph densities, and the average distance among brushes is first 1.8 and next 2.2. And we compare the results here. And the red line is the result I already showed. And the blue line is the new one at larger spacing. The appearance, we can see the appearance of the higher 1B1 peak. And this should correspond to some distortion of hydrogen bond. And very easy to understand that we should see some breaking of hydrogen bond. And this is a model. At 1.8 nanometers, they are completely tetrahedral coordinates, but 2.2 nanometers, we should see some distortion, the breaking of hydrogen bond on the surface in between the water core of the polymers. And there is a theory that said that at some bias, under some strong bias, there should be some ordering of hydrogen bonding. And the strength is, for example, at the 4.9 nanometers, it's about 500 kilovolt, very high bias. And this is possible because we have the counter anion and cations. And it should be some strong bias in between in the water surrounding the polymers. And that could be one of the origin of the ordering and the distortion of the hydrogen bonding. But we now start to see some breaking of hydrogen bond. So this explains that the effective bias is not enough to order all the water molecules in this low density polymer brush. And I will comment that this size may somehow correspond to the size of the nano ice. I don't know, but the order is the same. Using the same method, we can also do the measurements for the PMEA. And using the biocompatible PMEA and the reference TBUA, we subtract the spectrum for these two cases to extract the spectrum of this intermediate water. And the result is here. As you can see, the yellow line is the subtraction. And this is just in between the ice phase and the liquid phase. So just it's the intermediate. By looking from the electronic structure, the intermediate water is intermediate. So that summarizes my talk. It should be a good time. So X-ray spectroscopy is very sensitive to the number of hydrogen bonding and the distortion of hydrogen bonding. And so we can drop not only the bulk water, but the interfacial water. And now we are now applying this method to a lot of many kinds of water molecules in a very some circumstances. And this is very useful, and that can be compared with the other conventional IR, Raman spectroscopy, and our thermal experiments. So that's ends my talk. Thank you very much.
Thank you very much. Now, open for the discussion. Question, comment? Yes.
Thank you for your presentation. Which is the lifetime of the H bond that you use in your modeling?
Modeling.
Yes. Which is the lifetime, the estimated lifetime of the H bond?
Lifetime. Because our method is not assuming its lifetime. Because our method is measuring, for one spectrum we measured 1 hour or something, so we don't see any time scales. But what is your question? I don't answer.
Because I saw that in literature the H bond lifetime spans on 4 or 5 orders of magnitude, depending on the...
You think about the interfacial water? Yeah, so I just show you.
Yes.
Sorry. This one.
Make...
Oh, sorry, this one.
Oh, yes.
Yeah. But this is coming from the literature. I don't see anything.
You assume different time scale depending on the different kind of water.
But anyway, in our method we do not see any time scales here. Just this is from the literature, but we measure the average, time average of the structure. So I don't know. Yeah.
Thank you.
Thank you.
Any other question?
So I missed the polymers you used. Did they have oxygen in them? Because if so, how did you get rid of that? And I should have been paying attention when I was watching this thing, so I missed it.
Sorry, I don't know.
So the polymers you used, do they have oxygen in them? Yeah.
Are you talking about this?
Yeah, so how did you avoid seeing the oxygens in the polymer?
Yeah, we subtracted this. Yeah, this is a polymer.
Oh, okay, so it's not noticeable at all.
It's negligible, but
Yeah.
we already subtracted this spectrum. Yeah.
Okay, and the carbon didn't give you anything, or was it interesting, or
Carbon?
did you look at the carbon?
Carbon is very difficult to see. Yeah, but we can do it in a different station. But our station is actually the synchrotron not good at carbon because the mirrors and any optics has many carbons, and we have faced many problems to normalize the spectrum. So we do not do the
Yeah, with
study.
XES it can be less bad because you can choose a higher energy, but then you often...
Yeah.
Anyways,
Yeah, but we can do it. Yeah. So, but this time I just focusing on the water. Yeah, the both sides is very important. Yeah, I agree with you.
Any other question? Comment? So thanks again for the
Thank you very much.